Good afternoon, everyone. So welcome to my YouTube channel, Avatarm. So today we are going to see sixth lecture on functions of bounded variation. So let's start today's session now. If you have not subscribed my YouTube channel, subscribe it for such type of interesting topics. So let's begin our topic. So today we are going to give an example of a continuous function which is not functions of bounded variation. Okay. So example. There exists a continuous function on closed interval 0, 1 which is not of bounded variation. Okay, so I am defining that function. Define fx is equal to x into sine pi upon x if x belongs to open 0, 1 and 0 otherwise. Okay, this function f is continuous on closed interval 0 to 1. Okay. We will show that this function is not function of bounded variation. We will show it. So we are taking a partition for each n belongs to n. We define a partition Pn of 0, 1 by Pn is equal to 0. I am taking 2 upon 2n plus 1. Okay. Then next point is 2n minus 1, like that. Last 2 upon 5, 2 upon 3, and last one is 1. So this is partition of closed interval 0, 1. Okay, for each n belongs to n. Okay. So what is the SPN corresponding to this? So SPN of f. What is this? So this is f1 minus f2 upon 3 plus f2 upon 3 minus f2 upon 5 and so on, plus f2 upon 2n minus 1 minus f2 upon 2n plus 1. You take bracket here, plus f2 upon 2n plus 1 minus f0. Okay. So let's solve it. What you will get? You know that f1 value is 0 because sine pi is 0. Okay. So we have function. If x is not 0, I am to take the function x into sine pi upon x. So at x is equal to 1, it is nothing but 0. So it is 0, but sine, if I will put 2 by 3, it will be 2 by 3 into sine 3 pi by 2. Sine 3 pi by 2 value is, what is that? That is minus 1. So you will get finally, after taking outside the absolute value, you will get 2 by 3. Okay, here absolute value. Similarly, you will find here 2 by 3 plus 2 upon 5 here. Okay. Next one, similarly, you will get like that. Next one you will get, here I have not written anything, but similarly you will get 2 by 5 plus 2 by 7 here, like that. And continuing in this way, so continuing in this way, so where you will get here, you will get here 2 upon 2n minus 1 plus 2 upon 2n plus 1. Okay. And last will be 2 upon 2n plus 1. And sine this function f is at 0 is nothing but 0. So it will be 0 here. So adding all these terms, what you will get? So you will get here, this is here, 4 by 3 you will get. 4 by 5 you will get. 4 by 7 you will get here, like that. Okay. And 4 upon 2n minus 1 you will get here. And this is 4 upon 2n plus 1. Now you can take 4 outside. Now you can take 4 outside. So F, P and F is nothing but 4. This is 1 upon 3 plus 1 upon 5 plus 1 upon 7 and so on. 1 upon 2n minus 1 plus 1 upon 2n plus 1. Okay. Now you see that if I take this, this is this. So let's say this equation number 1. Now consider Fn is equal to 1 upon 3 plus 1 upon 5 plus 1 upon 7, 1 upon 2n minus 1, 1 upon 2n plus 1. Now we know that this sum is going to be infinity as n tending to infinity. Why? Because the series 1 upon 3 plus 1 upon 5 1 plus 1 upon 7 like that. This series is divergent and Sn is partial sum of that series. So this will tends to infinity. This tends to infinity as n tending to infinity. Okay. So by 1 what we will get? If this tends to infinity as n tending to infinity, from 1 what we get? From 1 we get S, P and F. This tends to infinity as n tending to infinity. Okay. So this implies supremum P belongs to row AB. Okay. Row AB. Row AB. SPF is greater than. Okay. So this is greater than So this stands to infinity as intended. Now next, since this is the supremum, so this will be greater than SPNS because PNs are certain PNs are partition of closed interval AB. Okay, closed interval AB. But this is the supremum over all the partition. So this will be greater. So when n tending to infinity, the lower thing tends to infinity as n tending to infinity. So obviously upper thing will be tends to where it will tends to. So this implies that supremum, this implies supremum P belongs to rho. So this is true for all n belongs to n. So this implies SPF is infinity. So this implies supremum P belongs to rho AB. SPF does not exist in R. So this implies F is not function of bounded variation. So this implies F is not function of bounded variation. This implies F is not function of bounded variation. So we have an example of a continuous function which is not a function of bounded variation. That is fx is equal to x into sine pi upon x if x is not 0 on the closed interval 0, 1 and 0 if x is equal to 0. So this is continuous function on closed interval AB which is continuous but not functions of bounded variation. Now I am asking a question to you. Question. Let Fn be sequence of functions of bounded variations on closed interval AB. Okay. If Fn converging to F uniformly on closed interval AB, okay, is Fn function of bounded variation on closed interval AB or not? If this is true, answer is no. Uniform limit of functions of bounded variation need not be functions of bounded variation. Okay. So we'll solve it. Solution. Answer is no. No. Why? Because we have shown that this function x sine pi upon x, if x belonging to open 0 to 1 close and 0 if x is equal to 0. Okay. In we have written this example in starting. Okay. So in in the place of otherwise you will write x is equal to 0. At x is equal to 0, it will be better. Okay. X is equal to 0. X is equal to 0. It will be better because we have to define only one single point. So x is equal to 0 will work here. Okay. So what we have, F is continuous on closed interval 0, 1. So we have a continuous function on closed interval 0, 1. And what is the statement of Weierstrass approximation theorem? If you have a continuous function on closed interval AB, there always a sequence of polynomials converging uniformly to F on that closed interval. So now same situation is here. F is continuous on closed interval 0, 1. Now by Weierstrass approximation theorem, theorem, there exists Pn, sequence of polynomials okay, such that Pn converging to F uniformly on closed interval 0, 1. Okay. But in last lecture we proved that each polynomial is function of bounded variation on closed interval AB. Since so in bracket we are writing that statement. Okay. In lecture 5, we have shown that each polynomial is function of bounded variation on closed interval AB. Okay, you take any closed interval AB. So polynomial is function for bounded variation. Okay. Because polynomials are defined on throughout real line, you restrict that polynomial, any polynomial on closed interval AB, then polynomial is going to be function of bounded variation. Okay. Now, so Pn's are polynomials. Each Pn function of bounded variation. On closed interval 0, 1. But we have just proved that F is not function of bounded variation but F Pn converging to F uniformly on closed interval 0. So we have an example of functions of bounded variation, that is Pn, that Fn converging to F uniformly, but F is not function of bounded variation. Okay, so this comes by Weierstrass approximation theorem. Okay, so today's lecture up to this. In this lecture, what we have learned? We have given you an example of a continuous function on a closed interval 0, 1, which is we have given an example of a continuous function which is continuous on a closed interval 0, 1, but that is not function of bounded variation. Okay, we also have discussed a question that if a sequence of functions of bounded variation converges uniformly to F on closed interval AB, is it necessary that F is function of bounded variation? The answer is no. Okay, Because the function we have given you, fx is equal to x sine pi upon x, defined on a closed interval. This is function of bounded variation. Okay, f is function of bounded variation. Sorry, f is not function of bounded variation. But by Weierstrass approximation theorem, we have a sequence of polynomials converging to f uniformly. Each Pn is polynomial. Polynomials are functions of bounded variation. And this sequence of polynomials converging uniformly to f, but f is not function of bounded variation. So this is the answer of this question is no. F need not be function of bounded variation. So today's lecture up to this. If you have any problem or doubt related to this topic, you can comment me on my YouTube channel. So thank you very much for today's session. Like, share, comment, and subscribe my YouTube channel. Thank you very much for today's session. Thank you very much.